Hello, everybody. My name is Lórien MacEnulty. I'm a first-year PhD student at Trinity College Dublin. I'm studying under Dr. David O'Regan in the Quantum Theory of Materials group. And in the course of my preliminary research, I've been investigating a little bit of PAW, the Projector Augmented Wave method. And so I wanted to discuss a little bit of what I've been going over, I suppose, what I found, and then also kind of introduce how it is related to DFT+U, the subject of which I hope will be represented in a different one of these series, I suppose. So without further ado, I'll go into a little bit of PAW and then just a brief introduction of PAW in DFT+U. So as I said, PAW stands for the Projector Augmented Wave method. It was developed by Peter Blöchl in 1994 as basically the problem that was that faced DFT theorists at the time is that the numerical treatment of core electron wave functions was highly encumbered by strong oscillations near the nucleus. And as an example, I just included up there the radial wave functions of Au11+. You can see that as you get closer to the nucleus, when R is equal to 0, these oscillations get very heavy, and the number of nodes makes it very difficult for DFT calculations to keep up. And so a lot of methods were being proposed at the time to solve this. PAW was one of them. PAW basically tried to simplify the numerical treatment that was done in a way that was compatible with pseudopotentials. That is to say that it split the treatment of these wave functions into a frozen core approximation and then the valence states. So the formalism in and of itself is, it starts with the assertion that there exists a true all-electron wave function, and that it can be linked to a well-behaved pseudized wave function by a linear transformation. So mathematically speaking, it looks something like this. You have your all-electron wave function on the left, which has quite a few aggressive oscillations near the nucleus. And using a linear transformation, you can turn it, go between now a pseudized version of that wave function, which has no or few oscillations near the nucleus. If you make this assumption, then you can take into account, you can derive physical quantities like the expectation value of a certain operator by sandwiching it between the transformation operator and its Hermitian conjugate. And that will give you a pseudized representation of this expectation value. You can then that follows quickly from there that if you take the variational principle for the total energy, you can get the pseudized equivalent then to the Cohen-Sham equation. That allows us to look at our density functional theory codes, and instead of looking for the ground state of our system in real space, we can actually look for that ground state energy in a version of pseudospace. So what then is this transformation operator? What does it look like? Well, we know that as a prerequisite, it has to modify the smooth pseudo-valence wave function within an atomic region in order to yield the correct nodal structure, the nodal structure for the all-electron wave function. To demonstrate, you see on the right here, we have a representation of an atom with a blown-up nucleus, and then around that we have an electron cloud of certain density. And inside this electron cloud, you can have your all-electron wave function, which has quite a few nodes, a lot of oscillations. But we recognize that this is only necessarily a problem inside the regions that are closest to the atoms. We only really need to modify that nodal structure inside those atomic regions. So then we define this cutoff. We define an atomic region then that with using a cutoff radius of some type, so it's a spherically symmetric around the nucleus, and you get this cutoff wave function. And inside that radius, then we can say that there's a pseudo representation of that wave function that smooths it out. It gets rid of all of those nodes. But outside of that wave function, then the wave functions are equivalent. Outside of that radius, the all electron wave function and the pseudo wave function are equivalent. What we've effectively done here is defined something called the augmentation sphere. It's exactly as we just said. It's a spherically symmetric region with a certain radius r that extends out of the nucleus of the atom on a certain site. And inside of that region, the pseudized wave function is well-behaved. It's a well-behaved projection of the all-electron wave function. But outside of that region, those wave functions are equivalent. So then T has to be something that looks like an identity operator plus the sum of these atomic orbital-based modifications. Mathematically speaking, we get this expression here. So before we go about defining what those modifications are specifically, we need to define the canonical basis sets that are intrinsic to PAW that you will likely have to interact with at some point when you're using PAW. So the basis sets then, they are used in order to define these modifications. We start with the first basis set, and that is the all electron partial waves. These are, they can be defined in basically any way, but they would be somehow in some form solutions to the real Schrödinger equation. The next one that you're going to define are the pseudo partial waves. So these are identical, of course, to the all electron partial waves that are identical, outside of this cutoff radius, but then they are smooth, well-behaved projections of the all electron partial waves inside of this radius. And then, of course, we need to define the actual mechanism that allows us to have these representations at all. Those are the projector functions. They allow us to dedicate our treatment just to the localized regions around the atomic orbital, such that they are centered around the atom. And yeah. So these are the three functions that we will use basically everywhere in PAW to define things. A little bit about partial waves. Partial waves are basically manifestations of the fact that we can decompose plane waves into an infinite series of spherical waves. And these spherical waves are called partial waves. So we take our plane wave and we decompose it into this infinite sum of a product between spherical Bessel functions and the spherical harmonics. And it's that product that can be defined as the partial wave. Okay, so just to illuminate and make explicit the relation between these three wave functions, I put up kind of a schematic here. Of course, we see that the pseudo wave function, the pseudo basis functions, and the all electron basis functions are linked by a transformation operator inside of the augmentation region, but outside the augmentation region, they're identical. But then, most importantly, the relation between the pseudized basis functions and the projectors, then we find that they are dual to one another. So their overlap is either going to be 1 or 0, based on how they've been formed. But then also inside the augmentation region, the sum of those projections is equal to 1. So we define these, we place these restrictions on these, and then we define those functions accordingly. Just as a side note, the subscript I refers to actually 4 things. It refers to R, the atomic site. It refers to 2 quantum numbers, the angular quantum number and the magnetic quantum number. But then it also refers to a plane wave index. So that is related to the way that we define the partial waves in the earlier slide. Once you have those functions, then we can definitively define our transformation operator T. So once again, we find that it's an identity operator plus the sum of our atomic orbital contributions now become the difference between the projection, so the all electron wave functions inside our augmentation region, and the pseudized basis functions inside our augmentation region. And so you find that translates directly to our wave function. We get that the total wave function is equal to the pseudized wave function plus this long complicated thing, which I will illuminate a little bit further here using this diagram. In a lot of PAW presentations, you'll probably see something along these lines. So we have on the very left, that's our all electron wave function, the reality that we're trying to simulate. We can say that that can be represented by the pseudized version of the wave function, which is easier to calculate, plus then the all electron solutions inside our augmentation region, and then subtracting from that the pseudized wave functions inside the augmentation region. So now that we have our linear transformation operator, we can define the rest of our system properties. Well, in reality, we know that the density is very important. And then in our representation of that in PAW is going to be formulated analogously to the way we did our wave function. That is to say that we have our density is equivalent to a pseudo density plus something called a one center charge density, which is the sum over all of the valence atomic contributions inside the augmentation region, minus the pseudized version of that. We do this exact same thing for the energy. The total energy can be represented by the pseudized energy plus the one center energy minus its pseudized representation inside the augmentation region. And just to reiterate, we are treating our core electrons differently than we do the valence electrons. In reality, we want to treat them the same, but that becomes very cumbersome very quickly. So we split it just as PAW splits it in terms of this equation. Just as a note, these one center charge densities and energies are treated on a radial support grid for implementation in the DFT codes. So how do we go about defining these basis functions then? We know that they exist and we know that we can do things with them, but then how do we define them? Well, we'll start with the all electron partial waves. Those are ideally going to describe valence orbitals, the relevant states that we're looking to treat. And typically they're comprised of products of radial functions and spherical harmonics. And those radial functions are typically of a polynomial form. I say typically because they can be defined via other means. Really, there's a lot of freedom here in terms of how you want to define these functions, as long as they accurately represent the valence orbitals and they make your calculations less cumbersome. An important thing to note here is that typically we only end up using one or two of these partial waves per angular momentum in DFT codes. You don't necessarily need more, although you can, in accordance with the infinite sum, the more that you have, the more accurate your calculations will be. This will come, however, at the expense of your computational costs, so bear that in mind. The pseudo partial waves are the next that need to be defined. And those are defined in kind of an iterative orthogonalization in a process just as much as the projectors are defined. The first thing you want to do is you want to define some type of localized pseudopotential. And then you put that pseudopotential inside a Schrodinger equation, the pseudized Schrodinger equation, along with the all electron partial wave energy state, and you will end up deriving from that then your pseudized partial waves. Those would be the solutions to that pseudized wave function. That will also be of polynomial form typically, but also again depends on how you define it. And then the projectors exist to ensure that the pseudo partial waves are indeed the solutions to the Schrödinger equation. But like I said, they are derived from a complicated process involving iterative orthogonalization in order to satisfy the properties that you're looking for. So here's an example of what this looks like. This comes from the PAW tutorial in Abinet, where it teaches you exactly how to look at these functions in the course of your DFT calculations. I've included the link up at the top in case you're interested. On the left, there's 3D orbital of nickel. And you can see, based on this graph, that the cutoff radius is going to be somewhere around 2.5. And the way that we know that is because the projector function goes to 0 around that point. And around that point, the pseudo partial waves and the partial wave align. They become equivalent outside of that region. Whereas one is kind of getting rid of a few of the nodes inside of that region. Now the 4s orbital on the right side kind of elucidates this a little bit more. Illuminates this a little bit more. And once again, you can see that the cutoff radius is going to be around 2.25 or 2.5, somewhere around there. And inside the region, within that augmentation region, you get a nice, smooth pseudo-partial wave that really does effectively get rid of the several nodes of the partial wave, the all-electron partial wave of nickel. So that's an example of how it manifests in calculations. But another way that we end up interacting with PAW in our DFT calculations is via the pseudopotential. So we know that we have to, when we use PAW, we have to use a specific type of pseudopotential. And you get PAW dataset generators that output pseudopotentials that are in forms that are recognizable by DFT codes. But what is exactly going on behind the scenes there? Well, the only difference really is that PAW constructs a pseudopotential using the chosen basis functions. And it does this in a way using a method that's analogous to Vanderbilt's ultrasoft pseudopotential generation, and a process which I'll describe briefly here. So the first thing that you do is you'll find a screened local potential called V sub local, which is equivalent to the actual potential beyond some radius R sub pseudopotential I'll mention. The next step is that you take your pseudo partial waves, which have been defined such that outside of the cutoff radius, they are equivalent to the all electron wave functions. Now keep in mind that those are not necessarily the same. They don't need to be the same cutoff radius for either of them. You take your pseudized partial waves, and you use them to generate a different set of functions modeled by x sub I, such that you get that that you're operating on your pseudo partial waves with the difference of, so you start with your orbital energy eigenvalue, you subtract from that the transformation operator, and then you subtract from that the local potential. And so you get these functions defined this way. You find what your projectors are in terms of those new functions, and you'll end up finding that you'll need the inverse of an operator P. You use that fact as well as the orthogonality condition between the two in order to define your operator P as the overlap between the pseudo partial waves and your functions here. You then take that operator P and you use it to define another function called D, where you now have that D is equivalent to the sum between the new operator P plus the eigenvalue multiplied by this function Q, which is an integral over the augmentation region of something called the pseudized augmentation function. You take then the two key functions, then your d sub ij as well as your local potential, and you effectively unscreen them. And the way that you do that is for the local potential, you subtract from it the Hartree and the exchange correlation potentials. For the d function, you'll end up subtracting from it the integral over the product of the pseudized augmentation function and the local potential. And then finally, you'll find that your pseudopotential is going to be this unscreened local potential plus the sum of the function d, the unscreened function d inside the augmentation region. So that's how you end up getting a pseudopotential out of it. But there is one other important thing to note about how PAW is implemented in DFT codes, and that has to do with the difference between the Blöchl versus the Kresse implementations. Shortly after Blöchl published his paper, Kresse and Joubert also published a paper in 1998 that took the Blöchl formalism and modified it to make explicit PAW's relationship to the already well-established plane wave and pseudopotential implementations in DFT codes. It went about this by rearranging some of the energy terms, as well as changing the treatment of the pseudized exchange correlation contributions. What it did was add something called the valence compensation charge density to the exchange correlation energy. And it did this in order to ensure that the pseudo density added the correct amount of charge moments. It accurately represented the charge moments of the system. The problem with that is that the compensation charge has the capacity to introduce non-canceling errors if it's not treated properly. And this was demonstrated by Holsworth and colleagues in 2 papers, which we'll describe briefly in the next slides. The Blöchl implementation, which is explicitly implemented in ABINET, you see the exchange correlation potential is a functional of two types of densities. That's the valence density and the core density. Whereas the Kresse implementation has an exchange correlation energy that adds another term n hat, and that's the compensation charge density. And Kresse is implemented explicitly in VASP and Quantum Espresso, although I think they have since modified their implementation somewhat in order to account for the fact that near, and you can see in this demonstration, this chart here, this figure here, that near the cutoff radius for various types of, so for example, this is the exchange correlation energy, you can get different, you can start to find some discontinuities, numerical discontinuities that will perhaps affect your calculations. And you can see that here, this is how the Hartree energy and the density are influenced by the addition of the compensation charge density. So to illuminate this further, Holsworth recognized that this has to do with the sign. Holsworth and colleagues recognize that this has to do with the sign of n hat. What is it, positive or negative? So for a spherical atom, for example, in the ground state, we know that the compensation charge density is proportional to an integral inside the augmentation region of the all electron density minus the pseudo density. And so, for example, in the case of sodium, this doesn't present much of a problem because the pseudo density is smaller than the all electron density, which means that the compensation charge density is positive. But in the case of cesium, the opposite is true. You can see that the pseudo density is larger than the all electron density, which means that the compensation charge density is negative. And when that's negative, that's when the discontinuities start to introduce themselves. So this is prone to happen. This is a quote from Holsworth specifically. This is prone to happen when the exchange correlation energy does go negative, and it happens more often than expected and yields surprising results. It affects the binding energy by a slight but noticeable degree. This error manifests more sharply in the derivatives of the total energy, notably the phonon density of states. So this is something to look out for, I suppose. So briefly, I want to just address how PAW is implemented in LDA+U, but kind of to transition over into that, I'll talk about the formalism. The implementation of DFT+U is initially formulated using the Blöchl formalism in the following paper written in 2000. That is to say that it does not explicitly include inside the exchange correlation potential, the compensation charge. So, but a cool thing to notice is that ABINA actually has a variable called use XCN hash, which stands for use exchange correlational with n hash to, it does that to distinguish exactly between the Blöchl versus the Kresse implementations. The default though, and the default that was represented in this paper, was that ABINA determines the use of the compensation charge density through the PAW dataset. Okay, so then what does PAW in LDA+U look like? Well, it looks pretty much exactly the same. You start with, you're concerned with the behavior of the energy as a function of the occupation matrix. So we define the occupation matrix then. And in terms of the PAW formalism, we're going to end up using our pseudo wave functions, right? So I added a legend here just for all of these values. We define the occupation matrix specifically for an atomic site that we'd like to treat. For example, in the case of nickel, we treat the nickel d orbitals. So the T would be the nickel specifically, and then we define it going from there. We get F is our Fermi distribution, and that's defined for a specific band index and for a given K point. And then you get the expectation value of this projection operator, the pseudized projection operator P, using the pseudo wave functions themselves. This makes things easy for us since we can compute this, since we know that we're computing this term for highly localized orbitals. We can assume then that inside the augmentation region, the projection of those basis functions is approximately, the sum of the projection of those basis functions is essentially equal to 1. So we can use that to expand then our occupation matrix as such. Now, if we can condense it, however, when we define the occupation matrix specifically to address the orbitals L sub u, so a specific angular momentum, on a specific atom T, where m is equal to mi and m prime is equal to mj. Just beware here that I and j now refer to 3 terms, the angular momentum, which will be Lu, and then a magnetic angular momentum, and a plane wave index n. So it condenses as follows then. We end up getting that the occupation matrix, those matrix elements are going to be sums of this density multiplied by the overlap between the radial parts of the pseudo basis functions of the specific indices, the plane wave indices Ni and Nj. So that makes things, that simplifies things a little bit for the formalism. So just as an example, this will be the last thing that I'll go into, an example of how this occupation matrix looks. I'll take a look at the nickel atom, for example. So let's say that we want to, inside our system, treat a nickel, the nickel d orbitals. Well, in those d orbitals, nickel holds 8 electrons. 5 of them are spin up and 3 of them are spin down. So we look at the spin up occupations, and those are given by exactly our matrix element equation that we defined on the slide earlier. Right now, then, we know that Mi and Mj are going to span across the magnetic quantum numbers for L sub u is equal to 2. That is to say that Mi is going to go from -2 up to 2. So there will be 5 of them for the spin up matrix because of because there are 5 spin up atoms. We assume in all of this that we have defined our projection operator in such a way that it has focused the occupation matrix onto the d orbitals specifically on inside our nickel atoms. Just for reference, I've put up the definition of the density here, which we found in the earlier slide. So visually, what does this look like? Well, it's going to give us a matrix, a 5x5 matrix for the spin-up occupations. Mi, as I said, is going to go over all of the magnetic quantum numbers, which correspond to the dxy, the dyz, the dz squared, the dxc, and the dx squared minus y squared orbitals. So those are all of those are all of the possible orbitals that an electron can occupy inside of inside the L sub u is equal to 2. We have the equivalent up on top in order to define fully our matrix. So we get our matrix here, and we know that the diagonal elements then are going to be our suborbital occupancies. Now, the cool thing about PAW, however, is that because of how the number of partial waves that we've used to define our pseudo wave functions, each of these matrix elements is going to be either a sum of 1 or 4 terms, depending on what the number we've defined for those pseudo partial waves. So typically, as I said before, we define it using only 1 or 2. So 9 is a bit much for that sum, but 1 to 4 is probably more appropriate. So that simplifies things for us. The spin down occupations are going to be the same, except that it'll be a 3x3 matrix now, because there are 3 spin down electrons. And so that's how we would go about defining those matrices. Now, from those matrices, however, we end up getting we're going to directly plug those into the energy functional, from which we will get now the energy from the Hubbard U term. And so I've defined that equation just here. We know that U effective is going to be the canonical U Hubbard U minus Hund's J parameter, and then we use it to precede then a multiplication of these occupation matrices, the trace specifically of those occupation matrices. And one thing I always like to highlight here is that we see that U is acting as a penalty function, right? Because depending on the suborbital occupancies of our occupation matrices, which are going to be fractional charge occupations, depending on how close they are to 0 or 1, then U effective is going to be the more of a penalizing function or less of a penalizing function. That is to say that if it is, for example, 1 or 0, then there is no penalty function awarded. But if it's closer, for example, to 0.5, then there would be a higher penalty function awarded. So that's all of the information that I have for today. I'd like to, of course, eventually go into more of the intricacies of LDA+U, but perhaps that's good for another presentation. So thank you all for listening. If you're interested, go ahead and follow the O'Regan group TCD on Twitter, or check out our website. Feel free, if you have any questions, to email me or my advisor, David O'Regan. Thanks so much.